Okay, so hopefully you all know, just a reminder, the quiz is going on right now. You have until like, I guess, starting counting now, you have 7 hours left. So anyway, let's get started. So today we'll go over definitions of limits, so we all know what they mean. So there is an important point in your professor's video that I want to maybe clarify. So this is a not right definition, but we sort of accept it for purposes of class, right? Because if you want to get to the nitty gritty, the definition of like the sequence definition of a limit is pretty awkward. So basically, if you consider like limit x goes to a from the left or from the right, like, I don't know. Let's just say from the left. So you want the sequence definition. I mean, if f maps like u to r, then intuitively you want to say this, right? Xn in u, and since we're coming from a from the left, xn smaller than a, then if xn goes to a, f of xn goes to L, right? So not equals, but goes to. So that's intuitively what you want to say, right? But sadly, this definition is wrong. So it's actually basically like the actual definition has something like actual definition, like there exists some, I'll just write interval in this case. There's some interval like a to b. Sorry, I should write, since we're coming from the left, b to a, such that for all xn in b to a, if xn goes to a. So the book denotes this by like the set S, the superscript S. So the reason for this, I think Neil explains it pretty well. So if you consider this, right? So I mean, I didn't really go over limits to infinity yet, but you can think of infinity as a left-hand limit, right? I mean, you can only approach infinity from like the left, right? You can't approach it from the right because nothing is really bigger than infinity. So basically, intuitively, you want to do this, right? Minus like divide out by x squared, right? So if we went with the not right definition here, I could have considered a sequence going to infinity, like -2, -1, 0, 1, dot, 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 right? Like this sequence is clearly going to infinity, right? It's getting bigger and bigger, like 1, 2, 3, 4, 5, 6, 7, 8, right? But this sequence no longer makes sense here, right? Because the problem is this point 0, sorry. The point 0 right here is not defined, right? So that's why we need this, like, we need to squish it in some interval like a to b or b to a. But for the purposes of the class, like this honestly makes the most sense to everyone. So I think in the video he said for the purposes of the class, we could just assume this. So we don't need to get into the nitty gritty of like the actual definition. So anyway, so let's get on to the, you know, what it means for limits, right? So let's say f, for the purposes, let's say f defined in some interval, or I should write on some interval. And we want to write out all the epsilon deltas definitions, right, for limit x goes to s, f of x equals L. Now, before we do that, let me write out for s plus and s minus, right? So what does it mean to approach s from the right, right? It's exactly what you think. For all epsilon greater than 0, there exists delta greater than 0, such that, so before we had like absolute value, right? So in this case, we're only approaching s from the right. So we want something like this, right? Sorry, s less than x less than s plus delta, right? We're only considering like one side of the ball, right? So like if like s was here, before we drew a delta ball, but now we only care about like this side, right? So such that for s less than s plus delta, f of x minus L is less than epsilon, right? And similarly, for limit x goes to s minus f of x equals L, it's the same thing, right? Except now you're going from on the other side of the interval, right? So s minus delta less than s, less than x, less than s. Sorry, if then less than epsilon. Yeah. So this will really be what you'll be using. So, okay. Any questions so far? Okay, so now let's go over, instead of left and right, let's go over all the other possibilities. So again, f defined, for the purpose of this class, like f will be like defined on some like interval. Yeah, you're not going to have some weird set f is defined on. So, okay, so let's consider this case, right? L finite first. So if L is finite, S finite. What does this mean? So this is exactly what, like the usual, I mean, you did what it, you know what it means for like continuity, right? Continuity is like change the L to f of s, but in this case, it's just L. So x minus s if x such that if, here we write, such that if x minus s is less than delta, f of x minus L is less than epsilon. So here is nothing, nothing bad. So now L infinite. So by infinite, I mean like positive infinity. So what does it mean for the limit to be positive infinity? So if you think about it, I mean, what is a way to say like your number gets arbitrarily big? Well, it means for any, you could think of it like for any number I choose, after a certain point, all my values are, bigger than that number, right? So if I chose like 1,000, at some point for small enough delta, my function is bigger than that value. And if that holds for every value I choose, then it's infinite, right? So here for all, s finite. For all m bigger than 0, there should be there exists, by the way. There exists delta greater than 0, such that if x minus s is less than delta, f of x is bigger than m. Right? Hopefully this makes sense, right? No matter what m I choose, if I choose a small enough delta, this the value of my function will always be bigger than that m. Okay. Now let's do L negative infinity, s finite. So here is opposite, right? I want to say at some point my function is smaller than any number you choose. And in this case, I mean, it suffices to choose 0. I mean negative numbers, right? So there exists, now let me just keep it a capital M. There exists delta greater than 0 such that if x minus s is less than delta, f of x is smaller than m, right? So yeah, okay, hopefully that's clear, right? To be at negative infinity, you need to be like, you just keep going down, right? So now what about s being infinity? So let me just start with L finite first, right? S, and then hopefully you can combine the two, right? S being infinity, right? S infinite. So what this means is limit x goes to infinity, right? So here, I mean, what happens if you take limit as x goes to infinity? So this just means that, right? What does it mean to like go to infinity? It means that for any value bigger than some number. So the role of like the capital M in the above case kind of takes basically the M has a role in the range, right? So now you want like something like that M greater than 0, but for like your domain. So it's gonna, so here if you look, your M affected like the epsilon part, right? Instead of this, you have this. But now since S is in your domain, you want something that changes your delta part. So here it's for all epsilon greater than 0, right? What do we want for it being infinite? Well, we want to say no matter what number I choose, if I'm bigger than that number, then the result holds, right? So there exists alpha such that for x greater than alpha, f of x minus L is less than epsilon, right? So basically, I can get close to L provided, I choose some alpha big enough, right? So, okay, so, and then L finite S negative infinity, it's the same, right? So there exists alpha such that for x smaller than it, f of x minus L is less than epsilon. Okay, so I trust you can all do the L infinite, S infinite. You just combine the two here. So instead of epsilon, you have M instead of like, yeah. Okay. So before I continue, let me go over basically the theorem of this section. Honestly, if you're going to remember something, remember this. So f defined on J without A on some interval J containing A, then we have that to check whether limit x goes to A, f of x exists. So this is pretty important, right? I mean, limit should not depend on the actual point, right? Limit, your testing value is getting closer and closer to the point. So it doesn't matter if f is not defined at the point A, right? So exists if and only if limit x goes to A from the right equals, like basically the limits exist and they equal to some number, right? So then so basically once you get these two are equal, you will get, let me write like this, which is equal to, right? So basically this saying the limit as x goes to A, f of x exists if and only if these two, the left and right limits exist and are equal. And if they're equal, then that is what your limit is equal to. So note that this might seem really obvious to you, but it's actually not, because if you think about it, right? If you think of A as being here, limit x goes to A, f of x just means x approaching A, right? there's no reason why x has to approach a from only from the left or only from the right, right? Like I can approach a like this, for example. So make sure you know like the order where I put the points. This is my first point in my sequence, second point, third point, fourth point, fifth point, sixth point, seventh point, eighth point, ninth point, 10th point. So you see, like I'm going to A, but I'm not coming from just the left or just the right, right? I'm coming from like both sides. So this theorem says it's enough to just consider like coming from left and coming from right. So you don't need to consider like these cases where you're oscillating between left and right. Okay, so any questions? So this is pretty big. So I mean, the way you prove this is some sequence thing, I believe. So okay, any questions? Okay, so from now on we'll just start doing problems. So liquid text. So let's start doing 20.1, right? So 20.1. So let's calculate limit to 0 first, right? Since I feel that that's the most interesting. So exercise 20.1. F of x is this, right? So we want to say limit x goes to 0 minus f of x, right? So we want to calculate this. So really quickly, let me just remind you, just absolute value of 1 is 1. Absolute value of -1 is 1, but let me just write negative of -1. So it negates the negative number. So here, right, if x is approaching 0 from the left, what values is x taking? X is taking negative values, right? If you're approaching 0 from the left, x is going to be some negative number, right? And what does absolute value do to negative numbers? Well, it negates it, right? So the goal, when you see an absolute value in the limit, you want to get rid of it, right? So absolute value of x when x is negative is just negative x, right? So this is just -1, which is this, right? And similarly, limit x goes to 0 from the right. Well, what you're going to see is this thing. In this case, if you go to 0 from the right, you're approaching with positive numbers, right? Like 0.1, 0.0001, 0.0001, right? So absolute value of a positive number is just the number itself, right? It doesn't, absolute value does nothing to it. So this should just be x over x. Yeah, so hopefully this is a good review of Math 2A. So, okay, so you see that the left and right limits don't exist, right? So you, so here you'll get that the limit go to 0. F of x does not exist, right? Because the left and right limits are not equal. So note I'm using this theorem, right? This theorem is if and only if. So it's really strong. So to check whether some limit exists, you check whether the left and right exist and are equal. So in this case, they're not equal. Okay. So anyway, so let's continue. So the limit to infinity and negativity is the same, right? Because here limit to infinity of 1 is still 1, limit to negative infinity of -1 is still 1. So that should be simple. Let's do something a bit harder, maybe. So let's do maybe 20.14. So exercise 20.14. So we want to prove that, so this is an example of using epsilon deltas. Prove that limit x goes to 0 from the right is 1 over x, right? Is plus infinity. Limit x goes to 0 from the left is minus infinity, right? So what case are we in? So let's go back. So we are in L is infinite and S is 0, right? S is finite. So we are in these two cases, right? So this one and this one, right? The first problem is L is infinite and second one is negative infinity. So we have to use this definition. But sadly, it's almost that, but it's from the right, right? So it wouldn't be absolute value of x minus s less than delta. It would just be one side of it, right? So we have L is infinity. So let's do this. Let's do 1 first, right? And then do 2. So for all m greater than 0, there exists delta greater than 0 such that, so instead of absolute value, since I'm doing the right limit, it's going to be 0 less than x less than 0 plus delta, right? So if I always forget the if then 1 over x is bigger than m, right? So if you want to be, not that precise, you just say choose 0 less than delta less than 1 over m. So you could do this, and then 1 over x is what? So then what? So let me write two things. So if this is true, we have that x from here. Let me just underline it. From the blue underline, x is less than delta, right? So what can I say about 1 over x? 1 over x is bigger than 1 over delta, right? Now, from here, I delta less than 1 over m, if I flip it, 1 over delta is bigger than m, right? So from here, I get this. So, sorry, this should be m. 1 over delta is bigger than m. And then you're done. So provided you can choose some delta between 0 and 1 over m, right? So you could argue this many ways. So the first way is just to say there's infinitely many rationals but in the interval 0 to 1 over m. So just pick delta to be one of those rational numbers. But let me remind you of a nice property. It's 4.6 in book. It's chapter 4. It's something called Archimedean property. So that is pretty much what we are using. So it says if a bigger than 0, b is bigger than 0, then there exists positive n such that na is bigger than b. Hopefully this is clear, right? I mean, if I give you two numbers, if I multiply it by some big enough positive number n, like one of them, the one I multiply is going to be bigger than the other, right? Like even if I have like 2 and a billion, if I choose n to be 2 billion, like 2 times 2 billion is going to be bigger than 1 billion, right? So this seems clear, but what we're going to do is we're going to apply it, right? So we're going to apply it to a being 1 over m and b equal 1. So this Archimedean property says there exists n such that n over m is bigger than 1. But if you flip it, if you multiply by 1 over n on both sides, this is saying 1 over m is bigger than 1 over n, right? So we choose delta to be this, right? So remember, I just need some delta less than 1 over m, right? So this delta will hold. So if you want to, so like, yeah, so it follows from Archimedean probably, or I think it's fine if you just say the interval 0 to 1 over m has some number, and then you just choose delta to be one of those numbers. Okay, so now that we're good with that, let's do the second part. Let's do, so this is 1, right? So let's do 2. Okay, so here, let's go back, right? So 2, I have a left limit and negative infinity, right? So right here, I have L is negative infinity and S finite. So it's gonna look something like, you know, like for all m less than 0, blah, 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 right? So let's write it out. So for all, well, what happened? So for all m less than 0, there exists delta greater than 0 such that, so here I'm approaching what? So I want the left side of the interval, right? So I want 0 to be the biggest one because I'm approaching 0 from the left, and then 0 minus delta, right? Like before, the right side was 0 plus delta, if you remember, right? The blue underline. 0 less than x less than 0 plus delta. So if we're going from the left, it's going to be 0 minus delta. Sorry, if then we want 1 over x right here. 1 over x is less than m, right? That's what we want. So how do we do this? It's the same thing. So hopefully you can all agree. Choose 0 less than delta less than 1. So same argument as before. So note, I need this negative sign, right? Because here, you can't just fast forward and say delta's, choose some negative, some small, like, let me say it this way, some close enough number to 0 that's negative, right? Because here, delta's positive. So your delta has to be positive. So in this case, since m was negative, I need a negative sign. So you choose delta such that this holds. And then it's just inequality game from here on, right? So from the first part, you get 1 over delta. If you flip everything, 1 over delta is bigger than negative m. So negative 1 over delta is less than m, right? Now, what do we know from, let me do it different. From here, from the green underline, we get that, we have that, so this, let me just box this. We have that from the green underline, negative delta is less than x. So 1 over negative delta is bigger than 1 over x. And then you're done, right? Because from here, from these two, from the two boxes, you're done, right? Because 1 over x is less than 1 over negative delta, which is less than m, right? So yeah, hopefully you all get the gist of proving limits. So if I were you, I would study this list, right? So this is pretty important. So okay, let's continue on. So let's do something harder. So let's do something more proof-based, right? So I'll try to choose even numbers, right? Because odd numbers sort of have solutions in the back. So let's do 20.16, yeah? Suppose the limits L1 and L2 exist. So exercise 20.16. Suppose, so we have two functions. L1 equals limit x goes to a from the right, f1 of x. L2 equals limit x goes, well, yeah, they're both from the right. So f2 of x. And exists, so both of these exist. And we want to show if f1 of x is less than or equal to f2 of x for all x in some interval ab, then L1 is less than or equal to L2. This seems intuitively obvious, right? Because if your function is always smaller than the other one, well, on the interval, well, when you go to a, like, it's still going to be smaller than or equal to, right? So, because one of them was always bigger than the other. So let's actually prove this. So the idea is, if we assume by contradiction, right, this was bigger than L2. So if I write here, here's L1, here's L2. Now, how are we going to get a contradiction? Well, we know the limit exists, right? So F2 goes to this, so F2, and F1 goes to this, right? Like that, because L1 is the limit of like F1 and L2 is the limit of F2. So eventually, F2 using the epsilon delta definition will be here, and F1 will be here, and we get a contradiction, right? Because that would mean F1 was bigger than F2. So that's the approach, right? So if you, that's like the picture approach. So hopefully we all get what we're trying to do. So how to do this is, well, let's consider this thing and take the midpoint, right? So let's let our epsilon be L1 minus L2 over 2, right? This is like the midpoint. Right? I mean, so like this, so that our epsilon has like this length. So this is our, right? This thing has length epsilon. Sorry, I shouldn't write this. So I'm taking like half the midpoint, right? So this thing has length epsilon. So what we're going to do? Well, we're going to apply, we know these two limits exist, right? So we have a limit definition. So using the fact that the limit of this guy exists, let's write it out, right? For this epsilon, there exists some delta 1 such that for, it's a right-sided limit, so less than a plus delta 1, f1 of x minus L1, sorry, minus L1 is less than epsilon, right? So epsilon is this, right? So let me write it here. But just to save space, I'm not going to write the L1 minus L2 over 2 yet. So, but just know epsilon, we're using the delta for this epsilon. Now, there exists delta 2 such that because this limit exists, right? So there certainly exists a delta 2 such that the F2 guy and minus L2 is less than epsilon. So such that for a less than x less than a plus delta 2, F2 of x minus L2 is less than epsilon. So we want both of these to hold, right? So both of these hold provided, you know, x minus a is delta 1 close and the second one is delta 2 close. So how do we make both hold? Well, we let delta be the minimum of delta 1, delta 2. Now both holds, right? Now both f1 of x minus L1 and f2 of x minus L2 hold, right? So now let's write this out, right? From here, what does this mean? So I'm gonna write 1 and 2 again. So 1 and 2. So let's work with 1. So hopefully you all know by now that being less than epsilon means this, right? Sorry. Yeah, epsilon and bigger than negative epsilon, right? So here, this means that L1 minus epsilon less than f1 of x less than L1 plus epsilon, right? So which one do I want? From the picture I drew, I want this side, right? And then for the F2, I want this side. Well, since I'm working with F1, I want this side of the interval, and that is this part, right? So here I have F1 of x is bigger than L1 minus epsilon. Now, what is this? So this is equal to, epsilon was L1 minus L2 over 2, right? So L1 minus L2 over 2. And what do we get? So what do we get? So we get L1 over 2 minus L2 over 2, right? Or sorry. Should be, is it plus? Let me think. So, right. Good. So we get this, right? Should be, because the minus distributes, yeah. So the minus distributes to minus L1 plus L2. Okay. Now let's go to 2 now. 2, from 2 we have F2 of x minus L2 is less than epsilon, bigger than negative epsilon. So again, we want to find the bigger bound, right? So we want the right side. So here we want, so from here, I mean, I just write this first. L2 plus epsilon, L2 minus epsilon. So we want this side, right? So from here, F2 of x is less than L2 plus, again, L1 minus L2 over 2, right? And what is this? This is exactly just L1 over 2 plus L2 over 2, right? So you have F2 of x is smaller than L1 over 2 plus L2 over 2. But f of x is big, F1 of x is bigger than that, right? So we get this. And that's a contradiction, right? Because we assumed that, we assumed F1 was smaller than or equal to F2. Yeah, so this is an example of, really, I don't think the important part is knowing how to do the question, right? I feel the important part is knowing how to work with in fact, it's just knowing the definitions of limits, right? Because once you have this picture, I trust you can all do it. Like this picture, like once you get the idea of how to prove it, it's the rest is writing it out formally, right? But once you have this, it shouldn't be too bad. So, okay. So I think that's one part of it. So part 2. So suppose that in fact F1 is smaller than F2 of x for all x in AB. Can we say L1 is less than L2? So let me just part B. So remember L1 is limit. L2 is this limit, right? No, sorry, this should still be A. I don't know why I wrote B. So if we know, so the question is, if this is true, is L1 less than L2? So how is this different from part A? So part A, there's an equality sign for, part A was this, right? Part A was, was basically this. But now we're taking off the equality sign, right? Because remember, part A was if it's less than or equal to, then less than or equal to. So now it's saying if it's just less than and we don't have it equal to, does the result hold? So if you think about it, the equality sign is necessary, right? Because if you think about it, even though a function is smaller than another, if you even think of something to infinity, right? If you have a function here that approaches this number a, I could still make a function that approaches a, right? But like that is like always under the other function, right? Like, because the idea is you can still both go to a, but at different rates, right? So like if you think about like x and x squared go to infinity, both go to infinity, but x, I mean, like, you know, eventually, I guess that's a bad example, but like after some point, like x squared is always above x, right? Because x squared grows faster. Like you can like always approach at infinity, but at like a different rate. So here, an easy example, I mean, would be something like, you know, f1 of x is like, let me think, like 1 minus 2x, and f2 of x is 1 minus x, right? I might have swapped it actually, but actually I think we are good. So let me think. Yeah, we are good. So my a is 0 and my b is 1, right? So clearly limit x goes to 0 from the right of 1 minus 2. I mean, the limit exists, right? So it's 1. And limit x goes to 0 from the right of, sorry, oh, this is f1 of x is, so clearly this is also 0, right? So the limits are actually equal. So here L1 is equal to L2. So it's not the case that L1 is smaller than L2, but it's pretty clear that on 0, 1, f2 of x is bigger than f1 of x, right? Because f1 of x, you're subtracting something bigger, right? So yeah, so that's a counterexample. So here the picture would look like something like this, right? You have two functions going to 0, one is on top of the other, right? So yeah. Okay, so before I end this, maybe just let me try to remind you, you know, let's do 20.11 part A and B. I just want to make sure you all know Yes. Sorry. Sorry. It seems like I lost connection or something. So, uh, hopefully everything's clear.